Imagine a bathroom that only one child can use at a time. If two kids try to go in together, they will bump into each other, and the bathroom will get messy. A critical section is like that bathroom. It is a part of a program where only one process or child may be inside at a time. We need critical sections whenever many processes share a common resource such as a file, a printer, or a piece of memory. Without a rule that says only one at a time, the processes could write on the same line of the file at the same moment, making the data unreadable, just like two kids drawing on the same paper at the same time would create a confusing picture. The intuition is simple. Protect shared things by letting only one process touch them, just as a single-person bathroom protects privacy and order. To make a bathroom rule work correctly, we need three promises. Mutual exclusion: only one child can be inside the bathroom at any moment. In a program, this means that at most one process can be in the critical section. Progress: if no child is in the bathroom and some children want to use it, one of them must be allowed to go in without waiting forever. In other words, the system should never get stuck when a process is ready to enter. Bounded waiting: a child should not have to wait forever while others keep taking turns. There must be a fixed upper limit on how many times other children can go before a waiting child gets its turn. These three rules together guarantee that the system behaves fairly and safely. We can think of them as traffic light rules at a four-way stop. Only one car goes mutual exclusion. If the road is empty, the first waiting car moves progress, and no car waits forever while others keep passing bounded waiting. Peterson's algorithm is a tiny set of steps that lets two processes, call them process 0 and process 1, share a bathroom safely. Each process tells the world it wants to enter by setting one I equals true. It then gives the turn to the other process. Turn equals j, where j equals 1 minus I, the other identifier. After that, it waits while both conditions are true. Want j and turn equals j. This means while the other process also wants to go, and it is the other's turn, stay out. When the loop ends, the process is allowed inside. This is the critical section. When it finishes, it sets one I equals false to announce it as left, allowing the other process to try again. In child-friendly language, each child raises a hand, want equals true, and then says you go first, turn equals other. If the other child also raised a hand, they wait for the other child's turn. When the other child either does not want to go or gives up the turn, the waiting child can finally go inside. The whole algorithm is just a few lines of code, but it follows the three rules above, guaranteeing safe sharing. One array of two elements equals false, false. Turn is an integer. Define lock function taking integer I. Set j equals 1 minus I. Want I equals true. Turn equals j. While want j and turn equals j, busy wait, do nothing. Now in critical section. End of lock functions. Define unlock function taking integer I, set one I equals false. End of unlock functions. Explanation. To prove Peterson's algorithm works, we look at the system state: a triple want sub 0, want sub 1 turn. The algorithm must keep two important invariants true at all times. Invariant 1, mutual exclusion, not want sub 0 and want sub 1 and turn equals 0 and turn equals 1. In simpler words, the state where both processes are inside the critical section cannot occur. Formally, if both want sub 0 and want sub 1 are true, then exactly one of them will see turn equal to the other's identifier, forcing the other to stay out. Invariant 2, progress. If want sub I becomes true while want sub not I is false, then process I will eventually pass the while loop. This follows because the condition want sub not I and turn equals not I is false immediately, so the loop ends. Proof sketch using state transition. Entry step: when process I sets want sub I equals true and turn equals not I, the state moves to true, want sub not I if want sub not I is false. The loop condition is false and I enters. Conflict step: if both set want true, the last right to turn decides who waits. Suppose process 0 writes turn equals 1 last. Then the state is true, true 1. Process 0 sees turn equals 1 is true and want sub 1 equals true, so it stays in the loop. Process 1 sees turn equals 1 is true, but its own test is turn equals 0, which is false, so it exits the loop. Thus only one enters, mutual exclusion holds. Exit step: when a process finishes, it sets its want a false, returning the state to a configuration where the other can enter. Because the change is visible to the other process, progress is guaranteed. Mathematically, the loop condition is the predicate P of I equals want sub not I and turn equals not I. The algorithm ensures that after each transition not P of 0 and P of 1 holds, proving the critical section can never be simultaneously occupied. Thus, by invariant preservation across every state change, Peterson's algorithm satisfies mutual exclusion, progress, and bounded waiting. The waiting bound is at most one turn. Peterson's algorithm assumes a sequentially consistent memory model. Every write is seen by all processes in the order it was performed. It also relies on atomic reads and writes to the two shared variables want array and turn. In hardware terms, those writes must be indivisible, like flipping a single light switch that cannot be partially on. If the hardware allows reordering of writes, common on modern CPUs, a process could write turn before it sets want index I equals true. Then another process might see the new turn value while still seeing the old want value, breaking the algorithm. Therefore, we need either a memory barrier or fence after each write, or to declare the shared variables as volatile, or use atomic types so the compiler and CPU treat them as non-reorderable. A write to a single word is atomic. Most CPUs guarantee this for aligned writes. The cache coherence protocol propagates writes to other cores promptly, for example, MESI. If a system uses a weak memory model like ARM's relaxed mode, the plain C version of Peterson's algorithm is not safe without extra barriers. Atomic one-word read writes. Sequential consistency or explicit memory fences. No compiler reordering of accesses to shared variables. When you code Peterson's algorithm in a real language, several hidden problems can appear. Number 1, compiler optimization. The compiler may cache the value of want of j or turn in a register because it thinks the variable never changes inside the loop. The busy wait then becomes an infinite loop. To avoid this, mark the variables as volatile in C or C++, or use std atomic with memory order relaxed for the reads and writes. Number 2, instruction reordering. Even with volatile, the CPU might reorder the two writes, want of I equals true, turn equals j, insert a memory fence, asm volatile m fence : memory on x86, or use atomic store with memory order release for want of I and memory order acquire for turn. Number 3, false sharing. If want 0 and want 1 share the same cache line, each core constantly invalidates the other's cache, leading to poor performance. Align the array to separate cache lines, for example Aligna's 64 bool want bracket too close. Number 4, starvation in real systems. The algorithm gives a bound of 1 turn, but on a heavily loaded system a process might be preempted many times, making the wait appear unbounded. In practice, higher-level primitives like mutexes handle scheduling better. Number 5, portability. Some embedded systems lack true atomic writes for the word size used. In that case, the algorithm is unsafe. A safe C++11 version looks like: declare atomic boolean array want of size 2, declare atomic integer turn, define function lock that takes integer I inside compute j as 1 minus I, store true to wanted index I with memory order relaxed, store j to turn with memory order relaxed, while wanted index j loaded with memory order acquire and turn loaded with memory order acquire equals j spin, end while, end function lock. Define function unlock that takes integer I store false to wanted index I with memory order release. Peterson's two-process trick can be expanded, but the direct extension becomes messy. The classic bakery algorithm, named after a bakery ticket system, generalizes it to n processes. Each process picks a number larger than any number currently in use, like taking a ticket. Processes enter the critical section in increasing ticket order. The algorithm preserves the three properties and works with only reads and writes, but it needs an array of size n and a way to read the maximum safely. Modern operating systems rarely use Peterson's algorithm because it relies on busy waiting, wasting CPU cycles. It needs strict memory ordering, which is hard on weak memory CPUs. Instead, they use hardware primitives such as test and set, compare and swap, or ticket locks, which are built into the CPU and guarantee atomicity. Higher-level constructs like mutexes, semaphores, and monitor objects are built on those primitives and provide blocking the thread sleeps instead of spinning, priority inheritance and deadlock avoidance. So while Peterson's algorithm is a brilliant teaching tool that shows how mutual exclusion can be achieved with only shared variables, real-world code prefers lock-free atomic instructions, or OS-provided synchronization objects for efficiency and safety.